You own 500 shops, 500 separate businesses, 500 separate towns, 500 separate managers who have never met each other. Every risk textbook ever written says the same thing about this. You are safe. 500 independent bets. If one dies, you lose 0.2% of your empire. The dots collapse. Here is how many bets you actually own. 1.36. Not on a bad day. Not in a crisis. That number is what your 500 shops are worth to you on precisely the day you need them to be 500. And it comes out of the same data you already have, using mathematics that has been sitting in physics journals since 1967. The last video was about the average being a lie. This one is about the second number, the one you use to prove you're diversified. And it's worse, because the average is at least a real quantity that you fail to receive. Most of your correlation matrix is a hallucination. Start with the thing everybody skips. Where does a correlation matrix actually come from? 500 shops means a 500 by 500 grid. Every shop against every other shop. Strip out the mirror image and the diagonal, and you need 124,750 correlations. Add the 500 variances. 125,250 unknowns. Now, how much data do you have? A year of daily numbers. 250 trading days times 500 shops. 125,000. Read those two numbers again. You have more unknowns than you have numbers. Not slightly fewer measurements than you'd like. Literally fewer data points than parameters. Every risk model in the building is solving an equation that does not have a unique answer, and it is solving it anyway, silently, every night. And the geometry is brutal about it. 250 days of data can only ever span 249 independent directions, which means 251 of your 500 directions of risk come out of the machine with a measured risk of exactly 0. Not small. 0. We're going to come back and stand inside one of those. Let's find out what that does to you. I built 500 shops that have nothing whatsoever to do with each other. Not weakly related. 0. Every single one of the 124,000 pairs is exactly, provably uncorrelated, because I generated them that way. Then I measured them the way you would. 250 days. Here's what came out. That spread is not a mistake, and it isn't noise in the casual sense. It's a law. The width of that bell is 1 over the square root of the number of days, 6.3%, and the measurement came out at 6.31. Physics on time. 6,106 of those pairs are statistically significant at the 5% level. 1,185 clear the 1% bar. And there is nothing there. There was never anything there. And this is the champion. Shop number 31 and shop number 181. Correlation of positive 0.25. That is the strongest relationship in the entire dataset. It's the pair your risk system flags. It's the pair an analyst writes a memo about. 2 shops in 2 towns that share a supplier or a customer base or a weather pattern or a story. It does not exist. I know it doesn't exist because I built the universe. And I could not tell from the data, and neither could you, and neither can the machine. So the noise is a law, which means somebody has already written it down. In 1967, 2 Soviet mathematicians, Vladimir Marchenko and Pastur, worked out what happens to the eigenvalues of a random matrix when it gets large. And if you don't know what an eigenvalue is, here's the only definition you need for the next 10 minutes. An eigenvalue is the amount of risk sitting in one independent direction. Big eigenvalue, big shared force. Small eigenvalue, quiet corner. Their result is this. If there is genuinely nothing there, no market, no sectors, no supply chains, nothing but chance, the eigenvalues don't scatter randomly. They form a precise, closed shape with hard walls on both sides. And the walls sit at 1 plus or minus the square root of q, all squared, where q is just the number of shops divided by the number of days. 500 over 250. Q equals 2. So the walls are at 0.17 and 5.83. Now watch this. Here are the actual eigenvalues from my 500 unrelated shops. Data, not theory. And here is the Marchenko-Pastur curve drawn on top. Nobody fitted anything. That curve was published 59 years ago. The largest eigenvalue anything achieved was 5.801. The wall is at 5.828. Chance walked right up to the line and did not cross it, which hands you the single most useful tool in quantitative finance, and almost nobody outside a handful of hedge funds uses it. You now have a line. Anything below it might be nothing. Anything above it is real. Now the real city. Same 500 shops, same 250 days, but this time I've built actual structure into them. A citywide economy that touches everybody. For industry sectors. And two weaker things I'll come back to, because they're the reason this video exists. Measure it. Take the eigenvalues. Put them on a log scale, because we're going to need the room. There's the bulk. 496 of them, sitting exactly where Marchenko and Pastur said pure chance would put them, in exactly the shape pure chance makes. And for escape, 113, that's the city. The tide that lifts and drops every shop at once. It is, in a very literal sense, the market. Then 13.7, 12.2, 10.8. The three sectors. That's it. That is everything the data can honestly tell you about 500 businesses over a year. There are four forces. 496 of your directions are indistinguishable from a coin. And here's the part that should stop you. Those 496 worthless directions are not a rounding error. They contain 70% of the variance you measured. Your risk model isn't slightly polluted by noise. Your risk model is mostly noise, wearing four real numbers as a disguise. One more thing while it's on screen, because it's the detail that separates people who use this from people who quote it. The market eigenvalue came out 0.6% above its true value, essentially perfect. The sector eigenvalue came out 30% too high. Big structures measure cleanly. Medium ones get systematically inflated, always upward, always in the direction that flatters your model. That bias is a known function, and correcting for it is a whole field. I said I built two more things in. Let's talk about them, because this is the part of the mathematics that I find genuinely frightening. 6 real structures went into that city. You found 4. The 2 you missed are called Cluster X and Cluster Y. They're real. 120 shops each, cutting across the sectors. Think a shared logistics contractor or a shared lender. In the true matrix, they are absolutely, unambiguously there. And they are invisible. Not hard to see. Not, we need cleaner data. Invisible, in a formal sense, with a proof. In 2005, Ben Aris and Pecci showed that a hidden structure only emerges from the noise if its strength exceeds the square root of Q. Below that threshold, the eigenvalue doesn't come out small. It doesn't come out at all. It stays buried inside the bulk, mathematically identical to nothing. There is a phase transition, like water freezing, and on the wrong side of it, information does not merely degrade. It ceases to exist. Our threshold is 1.41. Cluster X has strength 1.24. Cluster Y, 0.38. Both under. Both gone. So how much data would you need? Rearrange the condition, and the answer is T greater than N over a squared. Cluster X, 327 trading days. Fine. About 16 more months, and it surfaces. Cluster Y, 3,000 for 174 trading days. 14 years of daily data on 500 businesses, with none of them changing, none of them failing, none of them being acquired, and the relationship holding perfectly stable the entire time. 14 years. And by then it isn't Cluster Y anymore. It's something else, and you've just spent 14 years measuring a ghost. That's the honest limit. Not, we have bad models. Some of the risk in your portfolio is real, is currently pointed at you, and cannot be observed within the lifetime of the thing you're observing. Fine. Forget the invisible risks. Let's say you only care about the 4 real forces. What does the diversification you actually own look like? There's a clean formula. Effective number of bets equals N over 1 plus N minus 1 times the average correlation. Everything hangs on that one number, the average correlation, and it hangs on it violently. Calm conditions. Average correlation 0.22. Perfectly healthy, the kind of number that gets a portfolio approved. Effective bets, 4.45. 4.5. From 500 shops. In good weather. Stress. Correlation up to 0.46. 2.19 bets. Crisis. 0.73. 1.36. And now look at the shape of that curve, because the shape is the whole lesson. It doesn't decline. It falls off a cliff immediately and then flattens out. 99% of your diversification is destroyed by the first 20% of correlation. Everything after that is just picking over the corpse, which means diversification is not a thing you have. It is a thing that is quietly withdrawn from you at the exact moment you need it, by the exact mechanism that makes you need it, because whatever is scaring everybody is, by definition, a force that touches everybody. And a force that touches everybody is the market eigenvalue getting bigger. Put a price on it. 500 genuinely independent shops would give you a volatility of 0.0447. 1 over root 500, the number the textbook promises. 500 real shops give you 0.47. 10.6 times more risk than the diversification you believe you bought. You didn't buy 500 businesses. You bought one business, and then you bought it 499 more times. Remember the 251 directions with a measured risk of exactly 0? Let's go stand in one. I'm going to build a portfolio that lives entirely inside that dead space. Long some shops, short others, weights summing to 1. Nothing exotic, nothing leveraged beyond 9 to 1, and every ingredient is a boring shop you already own. Over the 250 days the model was fitted to, this portfolio has a volatility of 1.6 times 10 to the minus 15. That is not low risk. That is machine zero, the smallest number a computer can distinguish from nothing. A perfect hedge, flat as a table. Any optimizer on Earth, handed this history, will load into it as hard as you let it, because the math says the risk is not merely small, it is absent. Now let it run one day past the window it was fitted to. Volatility 0.64. And that's not a bad draw. Over 5,000 fresh days it holds at 0.64. A portfolio that promised 0 delivered a third more risk than simply buying all 500 shops equally and going to sleep. It didn't fail because the world changed. The world never changed. I generated the future from the identical distribution. It failed because the 0 was never a measurement. It was the shape of a hole in the data, and the optimizer found the hole and climbed in. 251 holes. Every one of them looks like free money. This is what people mean when they're being careful by the optimizer maximizes estimation error. It doesn't find the best portfolio. It finds the place where your data is thinnest and bets your firm on it. So what do you actually do? You can't measure the noise away. We prove the data doesn't exist. But you don't need to measure it. You need to stop believing it. Here's the fix, and it's almost insultingly simple. Take your eigenvalues. Keep the ones above the Marchenko-Pastur wall, because those are real. Take every single one below the wall, throw the individual values in the bin, and replace all of them with their average. You're not estimating them better. You're admitting you can't tell them apart, and forcing your model to admit it too. This is called eigenvalue clipping. Bouchard and Potters and Lalou at the end of the 90s. Let's give the raw model every advantage. For years of daily data, now instead of 1, Q drops to 0.5, twice the history. A genuinely comfortable data set. 4 spikes clear the wall, 496 get flattened to 0.72. Then build the minimum variance portfolio 3 ways and test all 3 on a future none of them has seen. Raw Markowitz promises a volatility of 0.33. Delivers 0.66. It understates its own risk by a factor of 2, with 4 years of clean data in a stationary world. Clipped promises 0.40, delivers 0.52. And the God Mode portfolio, built with the true matrix that nobody ever gets, 0.47. Deleting 496 numbers removed 22% of the realized risk, cut the gross leverage from 10 to 4.3, and landed within 9% of a portfolio built with perfect knowledge of the future's covariance. No new data, no new shops, no forecast, no cleverness. The only change is that 496 numbers were deleted for being fictional. If you saw the last video, this is the same move in a new suit. Kelly stopped optimizing an average you'll never receive. This stops optimizing a matrix you never measured. Both times the win comes from the same place. Subtracting a confidence you were never entitled to. Which brings us back to the bubble. Right now, there is an enormous amount of money spread across an enormous number of AI-adjacent names, and every one of those positions is defended with the word diversified. Different companies, different sectors, chips, clouds, models, tooling, energy, real estate for the data centers. But diversification was never about how many things you own. Run the matrix and ask how many eigenvalues that portfolio actually has, and the honest answer is that it has approximately 1, and the 1 is called the market believes this story. Every name in it loads on the same factor, and it will be the same factor on the way down, at the same time, for the same reason. Last video, the average was a lie because you only get one life. This time it's a lie because you only get one market. 500 shops. For real forces. 496 directions of pure imagination. And 2 structures that are genuinely there, currently pointed at you, and cannot be seen for 14 years. Diversification is not the number of things you own. It is the number of ways the world can hurt you separately. So the next time somebody shows you 500 names, do not count the names. Count the eigenvalues.